everyone, and welcome to another math tutorial. In this video, we're going to continue our discussion on solving quadratic equations. However, we're going to look at some previously unsolvable equations that are going to require a new system of numbers in order to solve them, and that system of numbers are called complex numbers. To provide us with a little bit of motivation as to why we need this new system of numbers, why we need complex numbers, let's take a look at a couple of review problems of solving equations that we've previously done within this unit so far. First one, we have 2x squared minus 90 equals 0. We're solving for x. So I'm going to begin by moving the 90 over to the right hand side. You get 2x squared equals 90. And we'll divide both sides by 2 to get x squared equals 45. And then to get rid of the square, we take the square root of both sides. We get x equals plus or minus square root 45. And then if we can simplify the square root, we're going to do that. So we get x equals plus or minus 45 is 9 times 5. So we get 3 square root of 5. Now, in this second problem, I'm going to essentially repeat the same exact steps just with different numbers. I'm going to start by moving this 120 over to the right hand side. So we get 3x squared equals, now this time because it's positive we have to subtract it, so we get negative 120. I'm going to divide both sides by 3, so x squared equals negative 40. And then we're going to square root both sides, so x equals plus and minus square root of negative 40. And at this particular stage of the problem, the fact that we've got a negative under that square root, anytime we've encountered that to date, we have stopped and said we have no solution. Now, we're going to dive into this particular type of problem today because it's somewhat dissatisfying to say that the problem can't be solved, to say that it has no solution. We want to be able to solve problems like this. So that's where we're going. That's the motivation for today, is so that we don't get stuck on this answer right here of no solution. All right, so what exactly is the problem? Let's formalize the problem that we're trying to be able to solve. Our issue or our problem is that we need a way to solve quadratic equations that result in a square root of a negative number. Okay, so that's what just happened in the last example problem, is that we had a square root of a negative number, and we said that that problem had no solution, which is partly true. So what is the solution that we're looking for? Well, we are going to need a number that has the property that when we square it, it equals a negative number. And so far to date, we don't have a number that does that. For example, anytime we square a number, let's just pick a number. Let's just pick a number at random here. Let's say that we pick 5. If I square 5, I get 25. If I pick the opposite of 5, if I pick negative 5 and I square it, I still get 25. So right now, every single number that we pick in our current system of numbers, if I square that number, the result is always positive. So we need a number that when we square it, the answer is going to be a negative number. So that's the solution. That's what we need to come up with. Okay, so what is the solution that we're looking for? Well, mathematicians just decided that we need a number that has this one particular property. And if we had that number, it would open up all these non-solvable quadratic equations. So we created a number to to have that particular property. Or in essence, we kind of expanded our number system. We created a new number that will do what we need it to do. So we call these numbers imaginary numbers. We denote them with simply the lowercase letter I, and it's simply a number that has the property that when we square it, or when squared, it's equal to -1. And I wrote that here in parentheses, but I'll write it here. So we created a number that has the property that when squared, it equals -1. Now that in turn gives the property that I, if I were to square root both sides, I is the square root of -1. Okay, so that's the number that we need. That's the number that we're going to use to solve these no solution type problems. Now before we jump into solving an equation, let's just take a few examples of simplifying square roots so we see how this new number is going to operate. All right, we have a couple examples on this slide. We're just simplifying the square roots. Now they're negative under the square roots, so we have to take that into account. Our answers are going to look just a little bit different to these problems than they typically have in the past. Now, -25, the way I'm going to think of this is as the square root of 25 times -1. And I can split that into the square root of 25, which we know, and the square root of -1, which we've just defined. Okay, so the square root of 25 becomes 5, and the square root of -1 becomes I, and we get the number 5i. Now, in practice, do I typically write this step and then this step before I get to the answer? Probably not. Once we do enough of these problems, you're going to be able to quickly go from this line all the way to that one, because we know 25 is a perfect square, that is 5, and because it's negative, it's just going to be the imaginary number 5i. On the next one, we have -40. So I need to split this up because 40 is not a perfect square. So a couple ways I can think of this. 40 is 4 times 10 times, and because it's negative, we have the -1. And if I split this up, then we've got the square root of 4, square root of 10, square root of -1. So this 4 becomes 2. This square root of -1 becomes I, and this square root of 10 is left over as the square root of 10. So I've got my answer like that. Another way that I typically do these kinds of problems, or when I think of them, is when I break up the 40 into 4 and 10. If it's negative, I just simply put the negative on the perfect square. So I'm going to do this as -4 and 10, and then the square root of -4 and the square root of 10, and then the square root of -4. Again, I don't typically, like over here, I said you're generally going to skip from here to here. I don't typically re-express this split up like this. I'm just going to say that the square root of -4 is 2i, and then we've got our square root of 10 there left over. Now, if you think you've got the hang of this and you want to go ahead and try these on your own, this is a great opportunity to just go ahead and hit the pause button and then resume playback when you've got the problems worked out. So let's go ahead and continue. I've got the square root of -72. So 72 is 36 times 2, and I'm going to put that negative on the 36. I'm going to put it on the perfect square. So now I've got -36 times 2. I have the square root of each of those. The square root of -36 is 6i, and the square root of 2 is left over. Next one, we've got square root of -500. So 500 would be 100 times 5. I'm going to put the negative on the 100 because that's the perfect square. The square root of negative 100 becomes 10i. I'm going to leave my square root of 5. All right, now we're back to solving quadratic equations. Now the equation below here is one that prior to this particular lesson, I either wouldn't have given you a problem like this, or if I did, you would have gotten to the point where you had a square root of a negative number and you would have told me no solution. But we're going to solve this problem all the way to its end. So we're going to begin by moving the 80 to the right hand side. So we have 4x squared equals negative 80. We're going to divide both sides by 4 to get x squared equals negative 20. And then we're going to square root both sides. So x equals plus or minus the square root of negative 20. Now again, previously this is when you would have said no solution. However, if we're being real picky, we should be saying no real solution, because in fact there is an imaginary solution. And so we're going to continue this on down to the imaginary solution, and we're going to finish this problem. So I've got now x equals plus or minus. Now I know 20, and this is kind of just my mental scratch work, but I'll write my mental scratch work here. I know that 20 is 4 times 5, and the square root of that one is 2. So as I simplify this, and because it's negative, I'm going to make this 2i, and then the 5 was the non-perfect square. So I get x equals plus or minus 2i square root 5. Our next example of solving a quadratic equation, again, I'm giving you one that prior to this video I would not have given you a problem like this because it doesn't have a real solution. We weren't ready for imaginary solutions, but now we are. We can go ahead and take this positive 25 and subtract it to the right hand side. Get quantity x minus 4 squared equals negative 25. We're going to square root both sides, so we get x minus 4 equals plus or minus square root of negative 25. Now we can simplify the square root of negative 25, and it's actually a perfect square. So we've got x minus 4 equals plus or minus 5i. We have our imaginary number now. And now we're just going to take this 4 and we're going to add it over to the right hand side. So I get x equals 4 plus or minus 5i. Now the 4 and the 5i, those are not like terms. This is a real number, this is an imaginary number, and so we cannot put those numbers together. We're just going to leave it exactly like that. Okay, next I want to dive a little bit deeper into this expanded number system, this new number system, right? And that last problem is a good jumping off point to this, because we had a solution of 4 plus or minus 5i. We had a solution that had a real numbered part and an imaginary part together. So I want to kind of talk about that particular number. Now, up until this video, right, and I've got a diagram here to kind of diagram some of this out, and then we'll come up to this definition here. But up until this point in your studies of math, right, let's put everything that you know into this circle right here. So everything you had up until this point were real numbers, right? They all fit inside that circle. And so some of your real numbers were like your counting numbers, you know, like 1, 2, 3, etc. Those are real numbers. You can include 0. So we go from natural numbers to whole numbers when we include 0. Negative numbers, -1, -2, -20, right? Those are numbers that you know already. Those are real numbers. We also have fractional numbers, right? We've got numbers like 1/2, 3/5, -2/7, etc., right? We've got what we call rational numbers, okay? We also have numbers that are irrational, okay? So the most famous example that you're probably aware of is the number pi, which is your 3.1415, the non-repeating, non-ending decimal, right? We have numbers like that too. So every number so far that you've ever encountered, they all kind of fit in this circle right here, okay? And that includes other kinds of numbers that I haven't even written down yet. That includes like square root numbers. Square root of 9, well, that's 3, that fits in here. Square root 11, that's an irrational number like pi, it fits in here too. But basically everything has fit into that circle. Well, at the start of this lesson, we had to solve equations that we couldn't solve before. Introduced a new system of numbers, and those system of numbers are called imaginary numbers. And there we've got numbers, not as many variants like we had real numbers, but we have numbers like 4i or -3i or square root of -18, like any square root of negative number, it's imaginary, right? So we've got these two distinctly different kinds of numbers. We've got real numbers over here, we've got imaginary numbers over here. Now, if you put these numbers together, we have another system of numbers, a brand new system of numbers. And that system of numbers are called complex numbers. Complex numbers are the combination of real and imaginary numbers. So you take one of these guys and one of these guys, and you put them together and you make a new number. For example, let's take 3, and let's take 4i, and we have what we call a complex number, okay? So that's how we define complex numbers. It's a number of the form a plus bi. Should probably say a plus or minus bi, because we could certainly subtract a number there, where a is a real number and the bi part is an imaginary number. Now, everything that you have learned, like in your life to this point, that you can do with real numbers, like addition, subtraction, multiplication, division, all sorts of things, right? All those kinds of operations and more than I just said, we can do with these numbers or these numbers as well. So we're going to take some time in the rest of this video to practice some simple operations with complex numbers. We're not going to hit everything in this video, and there's certainly going to be more that we'll hit in other videos on down the line, but we're going to start with a few kind of simple operations with complex numbers. Okay, we're going to dive right in with addition and subtraction. So we've got 7 plus 2i, that's a complex number. We've got 2 plus 6i, that's a complex number. And we're going to add these two complex numbers together. When you add and subtract complex numbers, it's really just an exercise in like terms. Okay? You can think of the I, the imaginary number, simply as a variable and just work the problem like you would any variable expression. So when I look at this, I look for my like terms, 7 and 2 are like terms because they are real numbers. And 2i and 6i are like terms because they are imaginary numbers. So I'm going to add the real numbers together. 7 plus 2 and get 9. And I'm going to add the imaginary numbers together. 2i plus 6i and get 8i. So I've got 9 plus 8i. So no different than I would work out any other type of variable expression type problem. In the next problem, we've got a subtraction of two complex numbers. We just have to be careful that the subtraction here carries to both of these numbers. So I'm going to identify my like terms. I've got 5 and 7, and then this minus 3i is going to go with this 2i. So here we go. 5 minus 7 is negative 2, and negative 3i minus 2i is negative 5i. Now, we just took a look at addition and subtraction, which are two of our four basic operations. Let's look next at multiplication. Now, again, just treat this like any other variable expression. And so if I gave you this problem right here and pretend that the i's were x's or whatever other variable you want to pretend they are, everybody watching this video would simply just distribute that 3i inside the parentheses. And the fact that they're imaginary numbers doesn't change what we're going to do. We're still going to just distribute. So 3i times 4 is 12i, and 3i times negative 2i is negative 6i squared. Now, we are working with complex numbers, right? And a complex number is of the form a plus bi. Notice that this form of a complex number doesn't have I squared in it at all. So I have to get rid of the I squared. Now, what do we know about I squared? Back to the very beginning of this video, we created the imaginary numbers based on the property that we were squaring a number to give me a negative number, right? We built this whole thing on the idea that I squared is equal to negative 1. So all we're simply going to do now is replace the I squared over here with negative 1. So it's going to turn the problem into this. We have 12i minus 6 times negative 1. So that's now 12i plus 6. And a lot of people are pretty picky about the order that you write these in, these complex numbers. We want the real number first, the imaginary part second. So I'm going to rewrite this to have 6 plus 12i. And that's it. Okay, our next example, we've certainly seen problems like this before. This is kind of just a FOIL problem where our i's are just the variable. So I'm going to take the first ones. 5 times 3 is 15. I'm going to take the outside. That's negative 5i. I'm going to take the inside, which is 6i. I'm going to take the last ones, which are minus 2i squared. Now we have some like terms right here. We're going to go ahead and put those together. So I have 15 plus I. Now we've also got an I squared, and we're going to pull the same trick, the same substitution that we did over on this problem. So I'm going to rewrite this as minus 2 times negative 1. So that I squared gets replaced with a negative 1. So now I have 15 plus I plus 2, and I have some more like terms now. We can put these two numbers together. 15 and 2 are 17 plus I. And it's even in my order that I want here, my A plus BI order. Now, as far as basic operations go, right? There's 4 basic operations. That's addition, subtraction, multiplication, and division. We are not going to do division in this video. We're going to hold that till a further, more detailed instruction on square roots and radical expressions. For this video, we're just going to do add, subtract. I thought I'd give you a chance on this slide to get some independent practice if you would like. If you want to hit pause and try these 3 problems out on your own and then resume play and check your answers, you're welcome to do that. If you think you've got this down, this is super easy. You can probably fast forward a couple minutes till you see the slide change and just skip over the slide. That's up to you. So I'm going to assume that you've hit pause, you've tried it on your own, and I'm going to go ahead and work through these problems pretty quick. We've got a couple of complex numbers. V is the number 3 plus 5i. W is the number 4 minus 3i. We're going to do V plus W. So I want to do 3 plus 5i plus 4 minus 3i. So I'm just putting like terms together. I'm going to have 7 plus 2i. Next one, we want 2 times w. So I want 2 times w, which is 4 minus 3i, minus v, which is 3 plus 5i. So let's distribute the 2 here. Will give me 8 minus 6i, minus 3 plus 5i. And now I'm going to go ahead and subtract my like terms. So 8 and 3, and then the i's. So 8 minus 3 is 5. Negative 6i minus 5i is negative 11i. Final problem, we have v times w. So we have 3 plus 5i. And multiply that by 4 minus 3i. So I'm going to go through my FOIL steps. I'm going to go through all 4 of these. So I've got 12 minus 9i plus 20i minus 15i squared. So I've got some like terms here. And this 15i squared, or this minus 15i squared, if I replace this I squared with negative 1, that term is really a plus 15, and so I've got like terms there as well. So 12 plus 15 is 27, and then my i's combine to give me 11i, and that's it. All right, next thing I want to talk about is the powers of I. We'll kind of make an observation here on this slide and then work out a couple example problems. Now we've only seen these first 2 right here, and we know that, well, I is equal to the square root of negative 1, but for the purposes of this slide, I'm just saying that I is equal to I. In other words, anything is equal to itself, right? On the next one, I squared, well, we know what I squared is. I squared is equal to negative 1, okay? Now, let's use those to build I to the third. I to the third power would be an I squared times an extra I. That I squared is negative 1 times that extra I. And so I to the third is negative I. And then I to the 4th power, well, 4 would be the same as I squared and I squared. Each of those I squareds are negative 1. Let's use parentheses here. And negative 1 times negative 1 is 1. Now, if I were to go farther, and I know I didn't write them there, but let's say I go a little bit farther. If I were to do I to the 5th power, I to the 5th power could be I to the 4th power times I, because 4 plus 1 more gets me back to 5. And I to the 4th power is 1. So this is just 1 times I, which is exactly what we started with, right? And so we see we're like right back at the beginning. And that's what's going to happen. We're going to have a kind of like a cyclic pattern here. I'm going to rewrite them over here for you. I is equal to I squared is equal to negative 1 I cubed is equal to negative I, and I to the fourth is equal to positive 1. And what's going to happen is every 4 powers of I are just going to repeat through this pattern. Okay, so I to the 5th was the same as I to the 1st. Start here. That means I to the 6th is this one. I to the 7th is this one. I to the 8th is this one. Then we go back up top. 9th power, 10th, 11th, 12th, etc. It just continues like that. So recognizing this pattern amongst our powers of I allows us to simplify much, much larger powers of I. For example, if I wanted I to the 27th power, well, if I were to use this idea again from the last slide, I just need to count this. I can, I don't need to. I certainly could. I could go 1, 2, 3, 4, and the powers repeat, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20, 4, 25, 26, 27. So I to the 3rd power is the same as I to the 27th power is the same as I to the 3rd power, which is negative I. Now, I don't always want to just kind of write these down and just count my way through them all because that might take a long time. So typically what I do is I take the power and I divide it by 4. Okay? Since every 4 it repeats, right? If I do 27 divided by 4, we get 6 and 3/4. So it goes in 6 times. That means I went through this cycle 6 times, and the remainder 3 is 1, 2, 3. It's how far I went on the next cycle through after I went through 6 times. So this is typically how I do it, is I just simply divide the power by 4, and the remainder I get tells me where on this list I want to go to. All right, so this example, we want to simplify I to the 102nd power. So if I take 102 and divide it by 4, well, 4 goes into 102 25 times, because 25 times 4 is 100, and that would leave me with 2 over 4 left over. I know that's reducible, but reducing it might confuse me as to which of the original 4 powers of I want. So I'm not going to reduce it for the sake of this is not really my answer, right? So I want the second power. I to the 102nd power is the same as I squared, and I squared is the same as -1. So I to the 102nd power is equal to -1. Okay, I want to show you one more thing concerning complex numbers in this particular video. And again, we're going to do some other things with complex numbers in other videos down the road. But for this video, this is going to wrap it up. You can actually plot complex numbers on a coordinate plane, right? We know how to plot real numbers on a number line. So this is no different. This is basically synonymous to plotting numbers on a number line, okay? So complex numbers need a complex coordinate plane. We have 2 numbers here, so we need 2 dimensions, right? We're going to call the x-axis, our traditional x-axis, as the real axis. And we're going to call the y-axis our imaginary axis. So if I want to plot these points, 5 plus 8i, I have to go to 5 on the real axis and 8 on the imaginary axis. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. That is 5 plus 8i. If I want to plot -3 plus 5i, I would go to -3 on the real axis and 5 on the imaginary axis. There's negative 3 plus 5i. If I want negative 8 minus 3i, I would go negative 8 in the real direction and negative 3 in the imaginary direction. And there's negative 8 minus 3i. All right, so final thing we're going to do now, using the graphing of complex numbers to find absolute value. So let's recall what absolute value is, right? Absolute value, the way we've always defined it in the past, is it's the distance from 0 on a number line. Well, really, absolute value is like the key part of that is its distance, right? So if I want to find absolute value of complex numbers, it's the same idea, but complex numbers do not plot on a number line. They plot on a complex plane, on like a coordinate system that we're used to. So if I want to find the absolute value of negative 7i, okay, first I'm going to plot negative 7i. Now negative 7i doesn't have a real number. It just has the imaginary number negative 7i. So that's going to come down here. Okay, so here's negative 7i. And instead of doing distance from 0 on a number line, we're going to do distance from the origin on the coordinate plane. So how far is that? Well, the distance from 0, 0 to 0, negative 7 is 7 units. And so that's our absolute value. Second example, we want the absolute value of negative 8 plus 4i. So I'm going to plot it first. Negative 8 in the real direction, 4i in the imaginary axis direction. So there's negative 8 plus 4i. And I want to know how far away is that number from the origin. What's that distance? Now, because this distance is on a slant like that, I can't just count through the boxes. But we know how to do problems like this. We've seen them before. I can create a triangle underneath it, a right triangle specifically. This right triangle has legs 4 and 8. And I can find this length by doing the square root of 8 squared plus 4 squared. I'm just doing Pythagorean's theorem. So I have the square root of 64 plus 16, which is the square root of 80. And 80 is 16 times 5. So my absolute value works out to be right over here and here. It's 4 square root of 5. All right, that concludes this video, this rather lengthy video, I know, on complex numbers. And believe it or not, we're just scratching the surface. This is just the very beginning of complex numbers. I want to thank you very much for watching this video all the way to the end. If you have any comments or questions, please drop them in the comments section below. I hope you have an awesome rest of your day, and I'll see you in the next video.